Hello students, today I am going to cover the topic canonical cover. It's a very important topic and lots of questions come on the canonical cover. We can call it, we can also name it as minimal cover or extraneous attributes. So we have to remove those attributes which or functional dependencies FDs which are not useful. Okay, so continuing on it. So what is canonical cover? A brief description. A canonical cover of a set of functional dependencies F is a simplified set of functional dependencies that has the same closure as the original set F. We can collect all the functional dependencies that can have the same closure as that of F. And what are extraneous attributes? An attribute of a functional dependency is said to be extraneous, means extra. Okay, if we can remove it without changing the closure of the set of functional dependencies. So closure should be the same. So if the functional dependencies do not affect the closure of the set, we can remove those functional dependencies. Okay. Now, the definitions of canonical cover. A canonical cover FC of a set of functional dependencies F such that all the following properties are satisfied. What are all the properties that we have to satisfy? First one is the F logically implies all dependencies in the canonical cover functional dependencies. So it should logically implies all the functional dependencies given in the canonical cover functional dependency. The functional dependencies in canonical cover logically implies all deficiency in F. So vice versa is true. Okay. So in both the cases, the minimum requirement of the functional dependencies should exist and it should have the closure of the functional dependencies. No functional dependencies in FC contain an extraneous attribute. So extra attributes are not required. So no functional dependencies in functional FC, the set FC contains an extraneous attribute. We should not have any extra attributes. Each left side of a functional dependencies in FC is unique. So left hand side should be unique. That is, there are no two dependencies alpha to beta, alpha 1 to beta 1 and alpha 2 to beta 2 in such that alpha 1 give you alpha 2. Like if we have two set alpha 1 to beta 1 and alpha 2 to beta 2. So this should not imply this. If it exists, then it will surely give you the extraneous attribute. So we have an algorithm to compute canonical cover of set F. So what we have to do? Use the unique rule to replace any dependencies in alpha 1 to beta 1 and alpha 1 to beta 2 with alpha 1 to beta 1 beta 2. So we can say that if alpha 1 to beta 1 is there or alpha 1 to beta 2 is there, then we can say alpha 1 to beta 1 or beta 2 can exist. Find a functional dependencies alpha to beta with an extraneous attribute either in alpha or in beta. So you have to find a functional dependencies alpha to beta. If we have any extraneous attribute, we have to find those in alpha or in beta. If extra is there, we have to remove it. If an extraneous attribute is found, delete it from alpha to beta until F does not change. Mainly the F, the closure should not change. We can remove any number of functional dependencies or set from alpha or to beta, but the closure should remain same. Next, we can do it by some example. Consider the following set F of functional dependencies. Like we have F, we have one set is A to BC, another is B to C, another is A to B, and next is AB to C. So, we have these mainly four set of functional dependencies available for a given relation. So, how to find the canonical cover? There are two functional dependencies with the same set of attributes on the left. Okay, we see that A to BC, A to BC and A to B. These two can be combined to get A to BC. These two can be combined. If we can have A to BC, then we can also have the A to B. Then the same thing comes like A to BC. We can say that. These two can be combined to get A to BC. Now, revised set of functional dependencies we can, after doing this step, we get A to BC same as this, B to C same as this, A to B, AB to C. We have removed this particular functional dependencies from here. This seems to us like it is an extra attribute. Okay. So, next is this. So, we have a revised functional set, it is given here. Next, what we have to do? There is an extraneous attribute in AB to C. Of how? We can see that. Because even after removing AB to C, from the set F, we get the same closure. If we remove AB to C, we get the closure. Okay. This is because B to C is already a part of F. Now, revised set of F becomes A to B and B to C. Like we have A to BC and B to C. AB to C we have removed it, because from B to C, from A to B we can go, and from B to C we can go. So, why we are using AB to C? As these two can easily provide you the set C, that the attribute C. So, we can remove AB to C. Next is the C is an extraneous attribute in A. How? Also, A, B is logically implied by A to B and B to C transitivity. So, we can say that if A to B is available and B to C is available, so we can go to C. If we are not using this C, then we can go to C. Okay. So, by the rule of transitivity, we can say that now we have these two attributes which will give you the same closure as in the first set F. So, after this step, F does not change anymore. So, the logical cover, that canonical cover, can be A to B and B to C. Let us have one more example. Consider another set of functional dependencies like F to A to F is given. One set is the A to BC, CD to E, B to D, E to A. So, here we can say that the left side of each functional dependencies in F is unique. We can see that A, C, D, B, E, all are unique. So, if all are unique, how come we remove the extra? How can we see something is extra? If it is repeated, then we can say it is extra. None of the attributes in the left or right side of any functional dependencies is extraneous. Mainly, we have checked. You can check all the rules that are provided before. We can check by definition of extraneous attribute on every functional dependencies. Okay. So, hence the canonical cover of FC is equal to F. So, here nothing is extra. So, we have the same functional dependencies, the same set of functional dependencies, it is in the canonical cover in FC. So, one thing to note, there can be more than one canonical cover FC of a set F of functional dependencies. Okay, so we can have more than one functional dependencies, more set of functional dependencies. We can have if we are removing something, we can remove anything else also in spite of the particular that attribute. So the set can be different. So how to check whether a set of functional dependencies F canonical cover another set of functional dependencies G. So we have to prove if it is a superset, subset, or it is equal. Like we have a second example, we have seen that it is equal. Okay, and in the previous example 1, we have seen it completely changed, and many extraneous attributes we have found, and finally we have a canonical cover in that. So consider the following two set of functional dependencies: A to B, AB to C, D to AC, D to E. This is one set, okay, and this is second set, okay, A to BC, D to AB. So first we go through this particular one, okay. Now we have required to find out whether one of these functional dependencies canonical covers the other set of functional dependencies. We have to compare these two mainly. Are the set canonical cover comes the same, or it is a superset, or it is a subset? We can see that. So this means we need to find out whether F canonical covers G, G canonical covers F, or none of the two canonical cover the other. Okay, one cannot cover each other. This can also be possible. So to find out, we follow the following steps. Create a singleton right hand side. We have to make the right hand side to a single part. This means the attribute to the right side of the functional dependency arrow should be all be singleton. Like we have the functional dependency D to AC gets broken down into two functional dependencies, that D to A and D to C. So we have a set A to B, AB to C, D to A, D to C, D to A. Now our set becomes like this. We have all the right side of the functional dependencies have become single. Now we have to remove extraneous attribute. So consider any functional dependencies x to y to z if x in itself can determine z. If we have a functional dependencies x, y to z, if x can itself can determine z, then what is the use of y here? So then the attribute y is extraneous and can be removed. As we can see, the occurrence of extraneous attribute is possible only in those functional dependencies where there are more than one attribute in the left hand side. So mainly we have seen if one attribute on the left hand side is given, then there are the possibility of extraneous attribute, but in combined form, if left hand side is not single, it's very rare to find that it is a extraneous attribute. So mainly we get the occurrence of extraneous attributes is possible only in those functional dependencies where there are more than one attributes in the left hand side. If there are more than one attribute side, then it is possible, like we have seen here, y is extraneous. So consider the functional dependencies AB to C, that AB to C, this one, okay. Now we must find the closure of A and B to find whether any of this is extraneous. So if we find the closure, A closure AB, B closure B, so B is only trivial, है? As we can see, B can be determined from A. B can be determined from A. This means we can remove B from the functional dependencies AB to C, as B can be determined from A. So we can remove this from the AC, A to C. So now we have become A to B, A to C, D to A, D to C and D to E. So now we are checking for redundant functional dependencies. Check all the functional dependencies one by one and see if by removing a functional dependencies x to y, we can still find out y from x and y some other functional dependencies. A more formal way to state that is to find the closure of x without making the use of functional dependencies. First, we have to find the closure of x, and by using it, by it will be used in the functional dependencies, and another time we remove those set from the list, and we can see that even after it is removed, it will give you the same functional dependencies or not, same closure or not. We are testing and checking whether y is a part of the closure. If yes, then the FD is redundant. So, here while checking for the functional dependency D to C, we observe that even after hiding it, the closure of D contains C. This is because we can obtain C from D by the combination of two functional dependencies, D to A and A to C. So, we can get D to C. So, why this is extraneous. Okay. So, A to B, A to C, D to A, D to A. Now, we have this set remains in our set in the functional dependency. So, now we can do for G also. This is the set we get for the one set of functional dependency that we have shown before. So, now I have to do the same for the G set. Create a singleton right hand. So, here A to B, A to C, D to A, D to B. We get, we make it in a singleton right hand side. Remove all extraneous attributes. Since right hand side of all the function contains only one attribute, there is no extraneous attribute possible. Means second step we have seen that all are singleton. If they are all singleton, that right hand side or on that right hand side, so contains only one attribute, there is no extraneous attribute possible. So, now the redundant functional dependencies, we have to remove redundant. By looking over all functional dependencies and checking the closure of the left hand side, in all the cases we observe that D to B is redundant, as D can from D to A and from A to B we can get D to V. So, we can remove this. So, now we have A to B, A to C and D to A. We didn't need required D to B. Now, since all the functional dependencies of G are already covered in F, we have concluded F covers G. Since, so the concluding remark can be, since all the functional dependencies of G are already covered in F, these all are covered in F. So, we can conclude that F covers Z. Okay. So, we have an example, we can also we do it here, like or you can have for practice session. So, first we have to do it to decompose, we have to make the right hand side in a singleton. So, we have x to w, w z to x, w z to y, y to w, y to x and y to z. Okay. So, what we have? These 5 sets or 6 sets. Okay. So, first we have to check whether this is extraneous or not, that we will do it afterwards, but we have to check this first. We have to find the closure of x, and what we get the closure of x? Closure of x can be x itself and w, and from okay we have xw. Okay, if we remove it, x to w, what we get? What we get? wz to from x we get only x, what else we can get? Nothing. So it is important. So it will stay here only. So this is required one. Then we check WZ to X. WZ to X, we find the closure of WZ. What will be the closure of WZ? It X W Z, X W Z, okay, X W Z, and from WZ we can get Y also. So X Y W Z, we all, if we remove this or hide it, we can hide it this, we can hide this and get the closure of WZ. Then what we get? We get W Z Y, or from Y we can get X. So it can be removed. This can be removed, right? And from here we permanently removed it. Next is the we checked WZ here also, whether it is extraneous or not. We can check what we get closure WZ, Y and Y to X we can get. If we remove this, what we get? If we remove this, what is the closure of WZ? We can get WZ. So it is required one, as it is not the same. So we required this one also. Now taking the closure of Y here. What will be the closure of Y? What will be the closure of Y? So Y, W, X, and from Y we can also get Z. And after hiding it, what we get? We get X, Z, we get X, Z, W and Y2. So this can be removed. This can be removed. Now checking for this set, what we get? X, Y, X, Y, Z, X, Y, Z, okay, and from X we can get W. If by hiding is, if we remove it, but if we can check whether we are getting the same closure or not. So here what we are getting? Y, Z, we get only Y, Z as it is removed, okay, no other means to find out anything. So this is the required functional dependencies. Now next to check this one, what we get? Y, Z, can get X also, from as it is available we can get X also and we can get W also. And after removing it, what we get? X, Y, X, Y, W, we get W only, X, Y, W. So this is also required. So we have these 4 functional dependencies set, but now we have to check for WZ. As in the right side also, there are some extra attributes are possible. So to check, we can get the closure of W and the closure of Z. What we get? The closure of W is W and the closure of Z is Z. So what the closure of WZ? What the closure of WZ? It's WZ. Okay, so these are different. If it comes the same, then one of them is extraneous. So what we can conclude it like, we have the final set as X to W, WZ to Y and Y to XZ. This is our final set. Okay, thank you. We have this much. Hope you have understood the concept of canonical cover. Thank you.